Hey, this is OXDF, and we're looking at day 24 of the 2016 advent of code as part of the 2023 revival of code. It's called Air Duct Spelunking. Let's take a look at the challenge. There's a bunch of story here about how we're climbing through the Easter Bunny's castle, but basically we're going to get into the HVAC system, and we're going to get input that looks like this, although much bigger, where the hash signs are walls, the dots are open spaces, and then numbers are these targets. So we start at target 0, and we have to find the minimum number of steps to get from where we are and get to each other target at least once. So in this case, they say that the answer is to go down to 4, back up, hit 1, hit 2, down to 3. So that's really it. That's all we got to do. Let's jump over here into VS Code. I'm going to go ahead real quick. We'll grab genday on 24. This is my script. I have details on all how it works and everything in the introductory video to this series. But the short version is it pulls the input and gives me some Python stubs to work with. If we look at the input, we can see it's much bigger than the example. I wonder if I can see if I zoom out here enough. Can we see it? So you can kind of see a maze in there. Let's make it bigger now. Anyway, there's a couple ways we can think about approaching this. We could do the first thing that comes to mind, especially given the way we've done this so far over and over again this year in the advent of code, is just doing a breadth first search. I will brute force every possible step. I will keep track of state as I go along. I actually don't think it's gonna be too bad. I think that's what we're gonna do. There's an alternative we could do, which is where we, instead of brute forcing all possible steps, we walk the maze and we find the shortest path between every 2 points. And then with that, we can do kind of a traveling salesman kind of problem. We can use path optimization algorithms, etc. Because I don't have to look up the ladder one, I think the ladder one's probably faster. Because we don't have to walk the whole maze once to get the distances, and then we can move from there. But I don't think a breadth first search is gonna be too bad, so we're gonna try it. And we might end up binning this video and completely redoing it if it's just a dumpster fire. But we're gonna go with that. So let's go ahead and take a look at, so I didn't mean to do that, day 24. Before we go to the tests, I'm gonna create a maze object. So I think, let's see if we can at least get rid of this. Class maze, and that's gonna hold the information about our, I'll pass it the puzzle input and it will parse it into, where the open spots are, where the walls are, etc. So I will do def under init. And we will also take in puzzle input. And I'm just going to leave it as pass for now. I'm also going to have def like run. And that will take self. And it will return, I guess, an int, because we're looking for the shortest path length. And also call pass right now. So now I've just got this I've got this object I can use. Now we'll go over and define our tests. I am going to create an example in a file, so we'll undo this. We're going to get example.txt here. We don't need to do any parameterization, so we can do this. That's part 1 on example. So what are we going to do? We're going to take AOC, not parse, but maze on example, and we're going to get back, we'll call it maze, and then we can say maze.run, and I guess we can say assert maze.run equals, and our example we'll need to grab it here, grab this, and it's 14 is the answer. So we can say we want this return 14. Then we better actually create the file. So there we go. Add an additional new line because I know the test data always seems to have it. That looks pretty good. Now, if I run this, I should get back none equals 14. Oops, wrong thing. I'm going to go up here and select PyTest from this debugging menu. I have a video where I show how to set this up, so I'll link that as well. But if we now hit F5, we run PyTest, we assert none equals 14, we're exactly where we want to be. Let's go ahead and actually define this. So first thing I need to do is parse my input. That's going to be the init. So what I'm going to do is I'm going to take self dot, and I'll call it like open spaces is equal to a set. And that'll be our set of spaces that we can walk in. And everything else will assume to be a wall. We can do self.targets. And this one, I want to keep where all the targets are. So I want to have both their position. I want to be able to map between the position and if the target's there. So what I really need to do is create a dictionary here where the key is going to be like the XY coordinate or the RC coordinate, and the result is going to be the target that lives there. That'll work because I want to keep both. Okay, so now we can do for r in puzzle input dot strip dot split lines. For C in, oh, actually, no, we need to, okay, so we need to enumerate that. So now I can have r comma line. So I'll get the line itself as well as the number of the line. And then here I can do for C comma val in enumerate line. So now I can now if val equals, let's see, if the val is, I guess the two options are that we have, I guess we have three options. We have a number, we have a pound sign, or we have a dot. So if val is not equal to pound sign or hash sign or whatever, then we're going to self.openspaces.add r comma c. So we add the point. Now we also want to check if it's an integer. So we'll do try target equals int val self.target r comma c equals target. And I guess we also need, okay, so then we can do except value error pass. So basically what I'm going to do here is, if it's not a pound sign, I'm going to add it to open spaces because I can walk there. And then I'm going to try to turn it into an integer. And if that fails, I just move on because that's probably a dot. But if it does succeed, then I store it in my targets list. And that might be all we need to do for init. Oh, we need to know where we start. And that is going to be, let's see, if target equals 0, self.start equals r comma c. So we'll basically just grab that way. I think that seems reasonable. We can add some tests here for parsing. So we can say, I probably should have done this to begin with, but let's just do it. Def test parse into maze. Example. We can say maze equals AOC dot maze example. We can assert. I better open up my example here. Like for example, we know start is going to be at 1, 1. So we have maze dot, start equal to 1 comma 1. That. What else are we going to know about this? Assert maze dot, oh, this should be upper, this should be lowercase. Oh, come on. Maze dot targets is equal to, I guess I can just quickly do this. So we know that the targets are going to be at 1, 1 is 0. So it'll look like 1 comma 1 colon the number 0. 1. See, so if we're going to do row is going to be 2, so 1 comma 1 2 3 is 1. Maybe instead of doing all these tests, because we kind of get the point here, right? We can say maze targets of 1 comma 1 equals 0. And we'll do one more for good measure. Maze targets of row 1 column 3 equal to, was that 1? Okay, let's try that. We should make these double equals, and we will F5. And we are failing here. Oh, we're still failing our second one, but we're passing our first test. So good, we've passed our initialization test. So now we can be on to the part 1. We have to actually do the breadth first search or do the run. Before we get to that, the biggest trick here in doing a breadth first search is going to be keeping track of state. So, as you know, in breadth first search, what I'm just going to do is define a queue with my initial state in it. I'm going to pop that off, and then I'm going to get all the next possible states, put them all in the queue, loop around, get the next queue, make sure I'm not complete, run it, put more things in the queue, etc. What I want to do is keep track of places I've been before. And I can't just say, have I been in this position before? Because, in the example here, I go down to 4 and then I go back up to 1, 1, and it's okay because that's actually part of the shortest path. So what I need to do is the state has to include the position as well as the targets collected so far. To make that easier for myself, I'm going to create a class. I'm going to do class state def under init. Let's see, a state is going to take an R, the targets and steps, and we're going to just do self.r equals r, so self.c equals c, self.targets equals targets, and self.steps equals steps. Now, what I want to be able to do with this state, I want to make sure that I can do things like it has to be hashable for me to put it into a set. So I'm going to define the hash to involve the things that I want to make it unique. So I'm going to do return hash, and it doesn't really matter how I set this up, as long as I set it up such that it doesn't include, for example, steps. I don't care about that. So I'm going to do self.r dot self.c dot string of self.targets. Again, it doesn't really matter what this is, but basically I've captured it such that if the targets change, the hash changes. If the steps change, but everything else is the same, it doesn't change. So that gives me that. I'm also going to do an equals here on self other, and that'll allow me to say, I'll say return self.r equals other.r and self.c equals other.c and self.targets equals other.targets. And this will help me be able to do with comparisons, like are these two states the same? The last thing I want is I'm going to want to, if I create these state objects and I store them in my queue, I'm going to want to be able to just get all the data out real quick. So I'm going to just do a def dump on self, and this is just going to return self.r, self.c, self.targets, self.step. Real quickly, I can just sort of get everything. Okay, now we can go on and do the brute force. So what are we going to do? We'll say, what's our initial state going to look like? It's going to be a state. We're going to be at self.start, so that'll expand out to fill R and C. The targets we've collected is going to be, I'm going to use a set. So we're going to have the target 0 because we start on 0. And our steps is going to be a number 0. Part of me wants to keep, in fact, let's try it. We're going to do an empty list. We're going to keep a list of our steps because it might be fun to animate this later. Okay, so we can say q equals, I'm going to work with a deck here. So we'll say from collections import deck. The q is going to be a deck of we'll take our initial state and that's it. Scene is going to be a set. We'll just keep that here. And I think that's all we need. So we can do while q. So there's something in our queue. There is now. State equals q dot pop left. We'll get the first thing off the queue. If state in scene continue. We loop around, we're done. Otherwise, we're going to scene.add state. And man, it's because we made this hashable hash function for state that we can add it to a set like this. Now we can say RC targets and steps is equal to state.dump. All right, so what are we going to do? Well, we want to see, are we on a target? So if RC in self.targets, then target we already have equals, and we want to add in, this is hard because so targets right now, we've we're keeping it as a set. We want to create, we want to add in, so we'll do like, we want to say targets dot union. And then we want to add in the new ones. We can say set on self dot targets r comma c, like this. We might need to put this. I don't think it'll hurt us to make this a list. So we're going to make a list of the target that we're adding. We're going to turn that into a set. Then we're going to union it with this target. So if it's already in there, it's not going to get any longer. If it isn't in there, it's going to, that way we're keeping our targets unique. If we hit something a second time, fine, it doesn't matter. Now we can say if len targets is equal to len self dot targets. So basically, we've got all the targets. Return len steps. We're done. Otherwise, we need to look for new ones. So we can say for dc in, and we'll just do a quick 0, 1, 0, -1, 1, 0, -1, 0. So basically, we can go in each of the 4 directions, and for each of those, we're going to say rrcc equals dr r plus dr c plus dc. Okay, so we've got the new position. Now we can say if rrcc in self.open spaces. So if we can walk to this new space, we're going to q.append. We're going to make a state. The state is going to be the new rr, the new row, the new position, targets, which may or may not have changed, and then steps plus we'll have to add rrcc like that. And I don't know, this might work. We will run till we get to all the targets. Let's give it a try. We can at least, the first thing we'll test here will be PyTest, so it'll test our example solution. Oops, I got a breakpoint here somehow. I don't know how that happened. Right click, run this. Ooh, we passed. That's exciting. Okay, I'm going to run this over to current file. We probably just, let's see if we probably have to change. So we have our maze object, we have our state. We don't really need this like part 1 function come into solve. We are going to say maze equals maze puzzle input. Then solution 1 is going to be maze.run. And I think solution 2 is going to be none because we don't know what it's going to be yet. We'll hit F5, we'll run it. And this is where it's not, I'm not sure how long it's going to take. In fact, let's pause for a second because we don't want to, I've shown in a previous video, I don't remember which, that it's actually much faster to run here. So let's, in fact, one more thing, let's run it with time and see how long it takes. That way I can pause the video if it starts to take a long time, or if I'm thinking about giving up. 8 seconds? That's not too bad. Like, I mean, I'd love to have a sub-second solution, but we can live with that. I guess we should see if it's right before we start spiking the football or celebrating too much. Awesome. Part 2. This is not long. I probably need to pause it. Let's see. What's the fewest number of steps required to start at 0, visit every non-zero number marked on the map at least once, and then return to 0? Okay. Doesn't seem too hard. Let's start with a test. I'm going to, we're just going to do this all as one walk. So what we really need to do then is we're going to change this to test run. We're going to get rid of you. We're going to have, we're going to say P1, P2 equals maze run. Now we can assert P1 equals 14. Assert P2 equals, and we better look at the example and figure out this. I mean, we shouldn't be too hard, right? I think the fastest way to do this now is actually just going to be to do a loop. Like, we can go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Oh, and then back to start, 19, 20. So 20 should be our full loop. So we'll just do that. We'll need to come over here and update this a little bit before we can even fail our tests. So let's look, make this solution2 equals maze.run, and we can get rid of here. And then we need to go up to our maze here and say, so what are we going to do? We're going to keep a part1 equals none. So here, if that equals steps, we can say if part1 equals, if not part1, so if it's the first time this is happening, part1 equals len steps. Now we can continue. What are we going to do if it, what's our end state otherwise? It's length targets equals length self targets, and then we can say if, and really we can just do r comma c equal to self dot start return part1 comma len steps. I mean, I didn't mean to just solve it originally, but let's see if we just did. F5, oh wait, I wanted to do this PyTest. Let's do our test first. F5 should be very quick. We're passing all our tests, so we are solving correctly. Let's come back over here to a terminal and run Python day 24. Again, I don't know how long this is going to take. I might pause the video here and come back. We'll see. I'm going to give it a minute or two because it is long. It could be as much as like twice as long maybe. And then, you know, when you're doing twice as long, many possibilities, you know, that wasn't even too bad. 14 seconds, not too bad at all. Let's grab 652. Awesome. Cool. Wasn't too bad. Okay. I've been playing around with this a little bit afterwards, and I can't, I wanted to show this. I think it's pretty cool. I went ahead and wrote an animation. So I'm shrinking this down a little bit so it will run nicely. Let's see. There we go. Now it's going to take its normal, what did it take? 16, 20 seconds, something like that before it ran. So it's got to solve the problem. But then it's going to pop up the animation on the screen and it's going to run the maze and it's going to show walking through that. So any second now. Okay, here we go. So the walkable spaces are in red and you can see the green dot moving through the maze. It's up here now. And it's about to collect 1. And when it collects 1, it turns green. Now, you know, so we hit 1, then 3. Now we hit 6 and we're moving through still. I've got it moving pretty fast because we could slow it down clearly, but it's a long maze and I'm going to be talking through all this. So I want you to see the end because the end's exciting. Not that I didn't do anything special at the end, but boom, we made it back to the end. So with an additional 30 seconds of maze, I thought that was pretty cool. Let me make my text bigger and shrink this down and show you all how I did it. So I need time because I got to do a sleep. So I added that. And I also brought in this term colored so I can colored from term color so I can make the colors nicely. I decided to keep the paths for part 1 and part 2 as part of the maze object. You'll see why in a second. So I don't need to define a part 1 down here anymore. I can just initialize it to none. And then here I set it to, you know, there. It might be smart in case I run it. If you were to ever run this twice in a row to just at the beginning of run, reset it to 0. But anyway, it works for this case. And then when I hit this, I'm going to grab steps, but I don't want to just copy, I don't want to just take steps and save it as part 1 because that is going to be like a pointer to the steps object. And then the object will keep changing. So by doing S for S in steps, I create a new list, which is now that new list gets stored in part 1, well, just what I want. Probably overkill to do it here in part 2 as well. But again, so then I can just return these 2 lengths, but having also cached those for later. And now I have this animate function, which just basically says, make sure there is a part 2. I get the max rows and columns from the open spaces list. I keep a list, I call it the GOT, of the targets that we've already achieved. That was just the easiest way. That's how once I stepped on a target, I can change the color. This is the print to clear the terminal. And then I'm just going to loop over. So for each step, I'm going to clear the terminal. I'm going to loop through rows and columns, checking each spot. If the row and column is the current position, I put this green box. And if it's a target, I append the target to got.append. Then if I'm not on the current step, if I'm on a target, if it's in got, I print it out as red on green. Otherwise, I print it out as green on white. And then I say, okay, we're not on a target and we're not on the current spot. If we're in open spaces, I'll show it as light red. Otherwise, I print it out as black. And then I put a new line here. When I get to the end of a column, I print a new line. When I get to the end of a row, I sleep for 1/100th of a second, not very long. But it still takes like 20 seconds to run the whole thing, so it's a lot of steps. Anyway, I thought this was cool. I'll run it one more time, just well, that one, we'll leave it there. Thanks for hanging out with me today. I appreciate you staying all the way to the end. I will talk to you next time. Bye.